will see the size here. See, already 10 MB, but anyways. Okay, so this is the introduction slide. You can talk about that. This is the topic, and you are this is your team at UC and AFRL, and we'll be talking about cooperative relative pose estimation to aid landing of an unmanned aerial vehicle on a moving platform. Okay. And this is the outline of the presentation. You will introduce the topic, formulate the cooperative relative localization problem, talk about the controller, show some initial results, and then you will conclude your talk. Okay. So this slide, you can add things to it later, but this is the most basic slide where you can start with UAVs or things like that. But the idea is smaller UAVs or small autonomous systems, when they work in group, has shown a lot of potential. Okay, like in search and rescue missions, surveillance, and so these missions need close coordination and control of autonomous vehicles. Okay, and in order to do close coordination and control, if you see, you need precise, accurate relative position between vehicles and relative orientation or relative heading, as a matter of fact. So you can see a couple of examples here. One of the example is this aerial recovery problem where a bigger mothership is flying at a higher altitude, which has a cable attached to it with a small drogue, and the idea is this smaller UAV, a MAV, will have to go and attach to this drogue. So you can see the problem that even if this drogue has a GPS and it can communicate its location, GPS has errors of 5 meters or more, so it won't be able to go and attach. So basically we need to estimate relative position between these two items. Okay, how do you do that? So that's one situation. Other situation, that the problem of landing UAV or a helicopter on a moving platform, something like ship, which is the problem of this paper. So we need to know relative position between these two vehicles and the orientation. Other problem can be your aerial refueling, right? So when this has to be really precise, where the drogue or the fuel hose has to go and attach to the other vehicle, so you actually need relative position, really nice, accurate relative position. The other problem of close coordination can be your formation control problems. Okay, so where again you are working in so close vicinity that you need precise position. So basically these applications show you the need of estimating relative position and orientation. Okay, so that's basically, you can spend some time here because this is where you are motivating the problem. Okay, so the next slide, I've left it for Anushna, and that you guys can explain. You need sensors to do any kind of estimation, right? So we have a standard sensor slide. You can include that you have maybe I can show you if those sensors are there. So this slide basically, so there are two type of sensor categories we have here. One is interoceptive sensors. So we have to include this slide. This is not there in the slide presentation. Okay. So something like an IMU, which has 3-axis gyros and 3-axis accelerometers, which basically provides you vehicle's motion information like acceleration and angular velocities. You can have wheel encoders on ground robots that can tell you, again, the same thing, linear and angular velocities. Okay. On the other hand, we have this exteroceptive sensors, basically to sense the external environment. Okay, how far the objects are, or what angle. So some of these sensors include a GPS, a laser rangefinder, a camera, a sonar, basically. So in order to do any, not just relative, but any kind of localization, you need to combine the information from these two type of sensors. Okay, so that is the basic idea here. That so the next slide, I think you can show this slide that, for example, GPS is a very common sensor. So if you only have IMU, you will drift. Basically, you're integrating your velocities and trying to estimate the position of the UAV. Okay. On the other hand, when you have a GPS, whenever a GPS reading comes, your uncertainty becomes smaller. And when you don't have GPS, you use again IMU information to integrate until you get a GPS measurement. So that's kind of basic localization process. But this localization is in inertial frame. You are trying to estimate where the vehicle is in with respect to the Earth center or northeast down position. Okay, so you can talk about this, and then so you be innovative. You don't have to use just that slide, but have talk about this stuff. You can include like picture of deca wave sensor and different time difference of arrival and all that stuff. Okay, then I would say that you can maybe just explain the difference between absolute, and you can say that absolute positioning is important for path planning purposes when you have to go from point A to point B. But when you are doing close coordination and control, relative position is more important. So our focus of this paper is relative localization. Okay. So now you can talk about that, explain the difference between relative and absolute, and then talk about related work. And that related work can include Hebai's work, your relative problem. So Hebai has introduced a problem where they are using relative pose sensors or bearing sensor to estimate relative orientation. Anushna has used range sensors to estimate relative position and relative orientation with a initialization method, because with using multi-hypothesis Kalman filter. Both of these works are for two-dimensional, okay, and they are less accurate. There can be trajectories, something like aerial refueling problem, where at the end your range becomes constant, right? Because you are maintaining a constant distance, that makes system unobservable. Okay, so now here you will have to read an observability. So maybe we need to send her a paper or something where you can actually understand what observability means and not means, and I might have some slides that I can send you so that you understand what observability means. Okay, like a formation control problem. So issue is whenever range, because range is the sensor that we are using to update our states, right? So if you are flying around a circle, or if you are maintaining a constant distance, then that range measurement is constant and it is not giving you new information. Okay, so that's why system becomes unobservable. And another thing is it is less accurate. We have seen that some trajectories will give you really, even if it is observable, the estimates are not good. And sometimes you cannot control that, because if I have to land or if I have to maintain a distance, there is nothing else I can do. I have to use that trajectory. So the idea of this paper is to use cooperative strategy to overcome these problems, both of accuracy as well as observability. And you want to generalize this relative localization problem to 3D. Instead of 2D, we are going to work in 3D. So this will be an important slide. Talk about what is there, what is relative localization problem, maybe a figure of your paper.
Okay. Yes.
Okay. Then in this here you say, okay, now you want to introduce the cooperative localization problem. You can introduce cooperative localization by giving this figure. Okay, so let's say for an example, 2 UAVs are flying. So instead of GPS now, so if you just if you just use IMU and just integrate to get the position, the uncertainty, the black ellipses are increasing, right, in size as the time grows, both sides. But somehow at if time t1 and t2 and t3, you can measure range between them and use that range to update the position of the vehicles, it will be better. But in this case, even though you are using range and even though these are better than just the IMU, they are still increasing. The red circles, if you see red ellipses, are increasing in size at t1, t2 and t3. So the idea is it is still unobservable. And it is unobservable because you're trying to estimate things in inertial frame and there is no information about inertial frame. So if this problem can be posed in relative frame, this can become, you can make this system observable and you will not need any absolute information. So you can put this figure and then maybe you can talk about previous work of cooperative localization, that you can represent the whole thing by a graph called relative position measurement graph, and where the vehicles are the nodes of the graph and the measurements between them, like range measurements, are the edges of the graph, and the stars are the known landmarks. Okay, so in this case we have shown in our previous work that one vehicle needs two landmarks for it to be observable, and we have also shown that if the graph is connected and every vehicle has a path to these two known landmarks, then the system is still observable. So there is a strength here. You're trying to show that even though this vehicle and this vehicle is not directly seeing any landmarks, but still the system is observable. So basically, by cooperation, you have increased the sensing range, the combined sensing range of the vehicles, and you still need two landmarks. And so that is the kind of that motivates you to use cooperation in your relative setting as well. So that is the idea we are trying to operate, and you can then show this video. Yeah, I am able to embed videos. Are you?
Yes, on Beamer. Yeah.
So maybe embed and then also give her. So in this, what is happening is you have two landmarks, landmark 1 and landmark 2. Their positions are known, and these vehicles are moving with black ellipses are the uncertainty, 3 sigma uncertainty things, and you can see that the estimated and true states are kind of close to each other, so that can be used for controlling and all that stuff. So that is the kind of idea where you can see this vehicle cannot see all the landmarks, all the two landmarks, but it always has a path to so that's why you want to use this kind of setting for our relative frame as well. So give a two vehicle problem, then maybe RPMG, then that's video, and okay, and then talk about limitation. The